Now that we have seen how hypotheses are formed, we actually need to go back to the Vapnik block diagram and actually start addressing one key aspect of it, which is the optimization block over here. So we've seen how the loss function, what is the loss function is with regularization. We've seen how we can potentially create various kind of hypotheses, and but we have not really discussed how we actually got this W star, how the optimal set of parameters got to be determined. And mind you that this whole discussion happened without really quoting even any probabilistic kind of concept. So we will finish this discussion first and by visiting an optimization algorithm called stochastic gradient descent. And then actually we'll go back into this diagram and start introducing again the same concepts, but in this time we will be discussing this learning approach from a probabilistic standpoint. Probabilities are going to be at the core of our learning agents from that point onwards. So the optimization algorithm that we're going to do see now is called gradient descent, and just to motivate it, I have actually drawn over here a simple function L of W. And this simple function is given by this expression of here is W squared. This is perhaps the simplest convex function you can actually have. And just to remind everyone about the concept of a tangent line at a point, here we see the tangent that touches, if you like, this function at this specific point. And I hope everyone remembers the simple gradients, simple derivatives from sort of your earlier kind of studies. And if not, we have sort of links in the math background module. This simple derivative of, I actually use here partial derivatives because typically we are going to have more than one variable, is approximated by the ratio of delta L by delta W. So here we see delta W. Delta W represents how much we wiggle the parameter W around that kind of point, and we observe how much the function changes as we vary that parameter by delta W. So that is going to be approximating for us the simple derivative, and we can actually calculate that simple derivative in general by plugging in the L, and we calculate the partial derivative of the W squared with respect to W. And from lookup tables, this is effectively partial derivative lookup tables, which are widely available, and we are going to provide in the notes a link for you so that you are familiar with such a lookup table, because we'll be using these lookup tables over and over again. You can actually see that this partial derivative is evaluated to 2W. And if you notice, as we are going to approaching this global minimum over here in this kind of function, and you can imagine that kind of tangent as the point is moving towards, if you like, the global minimum location, the tangent and the slope of that kind of tangent is becoming zero. So we can actually, given that this is the slope of that tangent line, we are going to set the partial derivative of L with respect to now W star. Now this W star is notation-wise represents the optimal point or the global minimal point in this case, and equal to 0, and that's a foundational theorem in calculus. And from that equation we can solve for W star and find as we expected, that global minima to be at 0. So this was a simple characterization of potentially expected behavior from an algorithm. This algorithm will actually function as follows. It will start from some initial random point, and it will actually gradually move in small increments towards the minimum. And actually, the analogy that we can make is that you are on the top of the mountain, and then there is a lot of fog around you, and the and you want to go down the mountain. You will have two options. One is to jump into the unknown at the expense of getting killed, and the second approach is to, since you can see a couple of feet around you, you can actually make the fall a small step, and when you reach that next step, you see again around you, make another step. The only thing that you need to make sure is that these steps are leading to a lower elevation as you're towards your target, to getting down the mountain. Similar things are actually happening over here. We are going now to see how we can express that as an equation, how this approach can be expressed as an equation, and explain that. So the equation for the gradient descent is the following. I am writing now the equation, which on the left-hand side has the next value of the parameter w. So this is the w, the initial w. This is the next parameter of the w, is the previous one, wk, minus a hyperparameter that we'll be calling the learning rate. And it's actually a small number, times the gradient. Don't be alarmed by this kind of nasty symbol. And this is the gradient of the loss function with respect to the parameter w, or the set of parameters w. So when we have many parameters, these are actually becoming vectors, and that's why we actually need to go into the next level up. So instead of a simple partial derivative, we have a vector of partial derivatives. So this is actually called the gradient of the loss function with respect to the parameter vector w. And this gradient is, as I said, the generalization of the partial derivative is a vector where we have, for a given vector of parameters that consist, let's say, of w0 all the way to w, let's say, m, we have the partial derivative of the loss function, or in any case any function, with respect to w0 all the way, partial derivative of the loss function with respect to wm. So that is the sort of functional form of the gradient descent algorithm. In other words, the gradient kind of generalizes the direction. In the simple case, where we have a single dimension, that direction is given by the slope of this tangent line. Now that we have in general multiple directions, we are going to have multiple partial derivatives. So if you can imagine, I'm sure everyone has used their hands to drink water from a water source. So as you are forming your hand, you create a cavity, trying to create a cavity. You have effectively two dimensions. One is along the direction of your fingers, and the other is the other direction over there, perpendicular to this. So these are basically a simple convex three-dimensional function that has been formed. It has two coordinates. One is the w1 and the other is the w2. And this is just a simple analogy to always remember when you're dealing with multivariate functions. And the partial derivative of using the first parameter and the partial derivative of using the second parameter will define that direction in the three-dimensional now space. So we'll see that in a notebook as an example a bit later, how this stochastic gradient descent, or sorry, gradient descent, it has not become stochastic yet, is able to find that kind of a minimum. So unfortunately for us, we will never going to have this simple situation of convex functions. Our loss functions are going to be very complicated and will involve billions and billions of parameters. And here in this page, we can actually see a great simplification of what is going to happen. Our algorithm is going to start from some kind of random point, let's say this point over here, and will start going down in small increments as we discussed. And it actually may get stuck into a local minima. And these minima are plenty. And actually, we're never going to have even the possibility of recognizing whether we got stuck in this local minima, which could be pretty bad. This local minima is much, much larger than the minima, which is the global minima that is at this point over here. And in fact, much, much larger even what is called a good local minima. So we have bad local minima and good local minima. At best, we would strive to optimize to come up with a value of parameter that corresponds to a good local minima. It's very unlikely it will reach, if you like, a global minima, that it's very difficult to find, as we are searching effectively in a huge parameter space in general. So this is something we always have to keep in mind as we are evaluating the behavior of this type of gradient descent type of algorithms. How the gradient descent is it going to help us optimize efficiently the loss function or not? And I want to address that kind of issue, which is associated with how heavy it is, so everyone gets to understand that kind of point, which is important. Is actually the pretext for us to introduce a more efficient version of gradient descent we'll be calling later stochastic gradient descent. So let's assume that we have a hypothesis. This hypothesis is a very simple hypothesis right now. It's just a straight line. I hope you remember from high school the equation y is equal to mx plus b. That's exactly the hypothesis we have here. We have some, in other words, data that this hypothesis makes sense for us to use. And we have obviously we have two parameters here, so we're actually having a vector of dimensionality 2. And I want to write again this kind of equation of gradient descent. wk plus 1 is equal to wk minus eta, the gradient of the loss with respect to w. And in this case, our loss function, and I hope you remember the loss function we have seen earlier, is the so-called mean square error. The loss function is, in other words, 1 over m. This summation from I is equal to 1 to m of y hat minus y, this is the ith prediction, squared. And if we replace the y hat with the shape and form of this hypothesis, the summation from I is equal to 1 to m of g of w comma x I minus yi squared. And this one is definitely equal to 1 over m summation from I is equal to 1 to m of w0 plus w1x minus yi, this is xi, minus yi, the whole thing squared. So what is we need to do now is to calculate the gradient of this loss function, which ends up being this one, with respect to the parameter vector w, which, as you probably remember from the definition of the gradient, I'm going to write it here at the top corner over here. So it is, this is the partial derivative of the loss with respect to w0, and then the partial derivative of the loss with respect to w1. This is the calculation we need to do. And actually, we need to see how heavy this calculation is at the end of the day. So we'll do the first calculation of the partial derivative of L with respect to w0. And it is going to be given by the 1 over m summation from I is equal to 1 to m, the partial derivative of w0 plus w1 xi minus yi squared with respect to w0. So if we're actually going to be evaluating a partial derivative such as this one, I think it was sufficient to go back to this lookup table of partial derivatives and recall, if you like, an identity that governs the partial derivatives of composite function. So I'm going to just put this in a box over here, this identity. And this identity reads that the partial derivative of a composite function, in other words, a function g that has arguments, another function f of x with respect to x, it is g prime f of x times the partial derivative of f of x with respect to x. Okay, so this is the definitely the a functional form of this kind of partial derivative that we will be using, and with a prime over here. In many textbooks, they are symbolizing the derivative of the function g. So over here, the composite function that we have is this squaring function, and inside it we have f of x. This is equivalent to what is inside that kind of parenthesis. So we'll apply the formula and see what we get. So what we get is 2 times the w0 plus w1 xi minus yi times the partial derivative of w0 plus w1 xi minus yi with respect to w0. And this is simply 2 w0 plus w1 xi minus yi, because the partial derivative of this is a partial derivative of w0 with respect to w0, which is 1, and all the other terms are actually 0, and therefore we don't write the 1 over here, so we end up with this. And this, of course, came from the fact that the partial derivative of something which is squared is 2 times that something, and this we have actually already met in that earlier discussion that we had about this nice convex function called w squared. Okay, so this was basically what we will be getting, this internal term with respect to the first parameter. And if we replicate this for the second parameter, w1, we will actually have exactly the same thing, 2 w0 plus w1 xi minus yi, partial derivative of w0 plus w1 xi minus yi with respect to w1 now in this case. And evidently this is given by the first term times xi in this case, because over here we have with respect to w1, so partial derivative of w0 with respect to w1 is 0, and then this of course gives us xi, and with respect to this is also another 0, so we end up with this expression over here. So what actually we see here is that this calculation is quite heavy. In many instances, we are dealing with pretty significant data sets in terms of hundreds of thousands, millions, if you like, of samples, of examples. And so M is actually typically very large. And for every iteration of the gradient descent, we will have to calculate this gradient quantity that involves itself a summation over all of our examples. So all of that calculation here is pretty complicated. So we have to go through the whole data set so let me write this down. We need to go through the whole data set. Let's call this data set of size M. M, of course, will be the M train or whatever portion of this data set we have allocated for training. So this is going through the whole data set. We call it one epoch. Okay, for each iteration, of the gradient descent, and we actually have to go through many epochs in order for us to be able to. When I say many, sometimes it will be tens of epochs. Each epoch involves M examples, so it is number of epochs times M of examples that we have to have as a total number of iterations. So I can write here the total number of iterations is number of epochs times number of examples, which I actually called M, so I don't need to write this down. Number of epochs times M. So these are the number of iterations we're going to typically have to execute. And this is actually a very large number when M is a very large number. And this means that for every of these each iteration, we have to go through one full sort of a visit through the whole data set M. So that's a very expensive, and we will be having to sort of find another an approximation which will end up actually also offering certain advantages as well. So we'll see that next. So in the stochastic gradient descent, instead of having to go through the whole M examples to calculate our gradient of the loss function with respect to W, as we discussed, what we will do is we will break down the M examples into what we will actually call the mini batches. So we're going to have to define a mini batch size. I will be calling this MB. And so this stands for mini batch. But sometimes people just refer to as batch. And we are going to, obviously this mini batch is numbers that could be as low as 1 to as high as let's say 4,000 examples, for example. It could be larger than 4,000. This is typically in this range, and in that this will be a hyperparameter. So mini batch is going to be a hyperparameter that we have to optimize in our so it's typically optimized as a hyperparameter. And this hyperparameter, you can actually use Optuna or whatever, any other tool that you actually have in order for you to sort of optimize such hyperparameters. We're going to have definitely either an assignment or another video that actually talks and walks you through this hyperparameter optimization. All right, so So this is the first step, is we're going to use for the gradient calculation only the a much smaller subset of our data to do the gradient calculation. And this is the initial algorithm, the gradient descent, sometimes actually called full batch. And in order for us to be able to make sure that we do not have anything systemic going on in our data, what we typically do is we are going to be sampling what kind of examples we are going to be selecting at every moment in time to form our mini batch. So either we have to, so let me write this down. We sample from the M examples to determine the examples that will form the mini batch, each mini batch, I would say. And the second thing that we do is, or alternatively, that's one way of doing it. Second way of actually doing it is that we randomize the order of our M examples. So we randomize the order of the whole data set that we have, and then we basically split it up into the integer number of mini batches. So these two obviously are equivalent, and in most cases these are delegated to the frameworks that we are employing, PyTorch, TensorFlow, and so on. Okay, so what we have achieved here with stochastic gradient descent. So let me just provide a picture that is always kind of useful to visualize what is really going on. We have, let's say, the earlier hypothesis that we have actually had seen this W0 plus W1x. So we have, for this specific hypothesis, G of W, x that we have seen earlier, we have two parameters. We have W0 and W1. So we are searching in a two-dimensional parameter space, which is actually shown here in this plane. Somewhere in this plane, there will be the optimal W star that we would hope to be able to find, as of course subject to the constraints that we had already discussed about how easy or difficult it is. But in this specific case, it should be straightforward because our loss function is well behaved. And we are starting, as we said earlier, from a so-called W0. So mind you, not confuse the W0 with the one of the parameters of the W vector. Here is the first iteration, the starting point of our W vector. So our W vector evidently has these kind of coordinates, W1 and W2. Okay, so here we have, in fact, I should have called them W0 and W1. W0 and W1. So these are our two coordinates. So this is the starting point. So earlier, what we have actually seen is that there will be some kind of a underlying sort of loss function, and I should have plotted that over here. There will be some minima somewhere. Let's assume that the loss function is such that the minima is actually located here. So that's our starting point. And we actually, earlier we were going into, broadly speaking, very broadly speaking and very approximately speaking, towards this direction to find that kind of minimum. Okay, so because of the fact that we were having a fairly well-educated kind of direction, I drew it as a straight line. Obviously, it's never a straight line, but that's a kind of an approximation I'm trying to convey here. So now with the mini batch, we are going to go into directions which are very noisy, because we are using only a small subset of our data for this type of estimation of the gradient. So our gradient estimates, which is the directional derivative that involves both parameters, will be fairly noisy. We may actually go into a fairly convoluted way, and we can actually show that still, if we choose the hyperparameter called learning rate as appropriately, to be able to still converge to the local minima, or the global minima for that matter. And that's one thing. So we're going to see some slower, I will call it, training in terms of, there's obviously the trade-off between computational efficiency to see exactly how slow it will actually be, and the form of the loss function. But we will see some kind of interleaved trajectory to reach that kind of minimum. Having said that, the advantage that we actually will see is that there is, in many instances, if you remember the presence of many local minima in real loss functions, that noisy gradient may actually help us escape from bad local minima and go to find new opportunities in the search space. So that noisiness help us find, perhaps it will help us find another local minima, which is actually a good local minima, and that will actually be okay for us. So despite the fact that we can, never reach a lower kind of local minima, that good local minima will be okay, and we will get some good performance out of it. So evidently the loss functions are not so well behaved in reality. So that stochastic version of the gradient descent is going to, has been found that it's performing very well. In fact, empirically what has been found is that gradient descent is a very bad algorithm for the typical machine learning problems we are going to be facing. So we are going to adopt stochastic gradient descent, which again empirically has been shown to perform much better for both computationally and also performance-wise on finding more opportunities for us.